Atlas instrument on ICESat-2 will measure heights on Earth by transmitting a pattern of 6 laser beams, receiving the laser photons that Earth reflects back up to the satellite, and recording the travel time of those photons. First up, transmitting the laser.
Hey there, I'm Tyler Evans, an optomechanical engineer working on the Atlas project for the ICESat-2 mission. So what we have here is the optical bench, which has a lot of the transmitter components on it, which is where the laser starts before it bounces off a bunch of mirrors and goes out towards Earth to measure ice. So the laser comes out of the box off of the fold mirror, and the fold mirror folds it 90 degrees, so it comes out towards the rest of the bench. Then it encounters this optic, which is the polarizing beam combiner, or the PBC, which sends the light in 2 different directions. So it picks off a small percentage of light to go through the periscope and into the laser sampling assembly. So one of the channels in the LSA is the start pulse detector, which is basically the stopwatch of starting and stopping that timer for how long it's going to take the photons to get back down to measure the ice and back. And that's really how the scientists are able to calculate what the elevation of the ice is by knowing that time that each of the photon travels. The rest of the beam comes out through the PBC out towards the beam expander. It hits the small mirror first, and it's 10 millimeters at this point. But when it hits this small mirror, the mirror has curvature to it. So what it does is it takes that 10 millimeter beam and it starts to expand it all the way out to 44 millimeters by the time it hits the second mirror. Once it hits the second mirror, it has curvature in it, which recollimates it. So now, instead of expanding, it's now staying at a constant size of 44 millimeters all the way out through the rest of the bench. It then goes through the beam steering mirror, which is right here. Atlas has a mechanism to be able to actually steer the beam and compensate for changes that might happen on the bench. So as the spacecraft goes in and out of the sun, thermal changes will happen to actually make the bench bend. And to compensate for those bends, you don't want to have the light bend as well. So we have a motorized mirror to be able to steer that beam so it's always pointing in the same direction no matter what happens to the bench. So the beam goes through the beam steering mirror, and then it actually goes through the DOE, which is the diffractive optical element, which sits right here under the bench. And it's a circular piece of glass, and it has an etched pattern in it. And that etched pattern basically takes that single beam and splits it into 6 different beams. So those 6 different beams then go out to Earth to be able to do the science.